This video covers Part 1 of Section 3.1, Proving Universal Statements. We'll start by discussing methods of proof briefly. The method of proof used to prove a mathematical statement is determined by the statement's logical structure. To determine the logical structure, we write the statement in symbolic form, so this is the first step in the proof of any mathematical statement. Almost all of the statements which you'll be concerned with proving in your mathematics courses will involve one or more quantifiers. So we want to begin our examination of proof techniques by discussing first, in this section, how to prove a universal statement, and second, in the next section, how to prove an existential statement. The overwhelming majority of mathematical theorem statements are universally quantified statements of the general form for all x p of x, where the propositional function p of x may be either simple or compound. We may also have more than one variable involved. The universal statement for all x p of x is true, provided that the propositional function p of x is true for all elements x in the domain D. So to prove the statement for all x p of x is true, we need to show that for each element x in the domain D, the propositional function p of x is true. There are two basic approaches to proving a universal statement, proof by exhaustion and proof by arbitrary element. So we'll start by looking at a proof by exhaustion. When the domain D is a finite set, we can prove that for all x p of x is true by systematically checking that p of x is true for each x in D. This method of proof is called proof by exhaustion. In order to carry out a proof by exhaustion, since we need to verify p of x is true for each element in the domain must be finite and relatively small. Sometimes we may be able to use a computer, in which case the domain can be relatively large. It must still be finite, however. We'll start with two examples of proofs by exhaustion. For our first example, we want to prove for all positive integers n with 1 less than or equal to n less than or equal to 10, n squared minus n plus 11 is a prime number. We'll start by defining the propositional function p of n will be n squared minus n plus 11 is a prime number. The statement then has symbolic form for all n p of n, where the domain for n is the set D containing the integers from 1 to 10. So we're going to use a proof by exhaustion. We need to verify that p of n is true for each value of n in the domain D. Substituting each value of n into the propositional function, we have p of 1 will be 1 squared minus 1 plus 11, which is equal to 11, is a prime. 11 is prime, so we can conclude that p of 1 is true. P of 2 will say 2 squared minus 2 plus 11, which is equal to 13, is a prime. 13 is a prime, so P of 2 is true. P of 3 says 3 squared minus 3 plus 11, which is equal to 17, is a prime. And we know that 17 is prime, so P of 3 is true. And we just continue this way for each of the elements of our domain. We have P of 4, P of 5, P of 6, P of 7, P of 8, P of 9, and P of 10. Since each of these statements is true, then for all n, P of n is true, which proves this statement. The polynomial n squared minus n plus 11 in this example is an example of a prime-generating polynomial. There are many other such polynomials that give distinct primes when evaluated over a range of values of n. The best known such polynomial is n squared plus n plus 41, which gives distinct primes for all values of n from 0 to 40. The only way to prove a certain polynomial is a prime-generating polynomial is to use a proof by exhaustion. For the next example, we need to first introduce a definition. This is taken from number theory. Given an irrational number alpha, one thing we might be interested in is finding a rational number that approximates alpha. One way to find such an approximation is to use the decimal expansion. For instance, since the decimal expansion of pi is 3.141592653, and it continues on indefinitely, then 314 over 100, 3,142 over 1,000, or 31,416 over 10,000 are all rational numbers that approximate pi. What we are really interested in, however, is a rational number with as small a denominator as possible. This is the motivation for the following definition. So let alpha be an irrational number. A rational number a naught over b naught is called a good approximation to alpha, provided that for every rational number a over b with 1 less than or equal to b less than b naught, the absolute value of alpha minus a naught over b naught is less than the absolute value of alpha minus a over b. And we assume all rational numbers are in lowest terms. Now note, the absolute value of alpha minus a naught over b naught is the distance between alpha and a naught over b naught on a number line. And the absolute value of alpha minus a over b will be the distance between alpha and a over b on a number line. The inequality in the definition then means that a naught over b naught is closer to alpha than any rational number a over b with a smaller denominator. For our example, we want to show that 13 over 4 is a good approximation to pi, according to our definition. To show this, we need to show the condition in the definition is true with alpha equals pi, that's our irrational number, and a naught over b naught is 13/4, that's our rational approximation to pi. So we need to show for all a over b, the absolute value of pi minus 13/4 is less than the absolute value of pi minus a over b, where the domain for a over b is the set of rational numbers with 1 less than or equal to b, strictly less than b naught, which in this case is 4. So to find the propositional function p of a over b will be the inequality the absolute value of pi minus 13/4 is less than the absolute value of pi minus a over b. So we need to show for all rational numbers a over b, p of a over b is true. We want to use a proof by exhaustion to show that p of a over b is true for all rational numbers a over b with 1 less than or equal to b less than 4. That is, with denominators b is 1, 2, or 3. Now there are infinitely many such rational numbers, so at first glance it doesn't appear we can use a proof by exhaustion. However, as we'll show, we only need to show that p of a over b is true for the rational numbers with these denominators that are closest to pi. For instance, the two rational numbers with denominator b equal 1 that are closest to pi are 3 over 1 and 4 over 1. If we show that 13/4 is closer to pi than both 3 over 1 and 4 over 1, then it follows that 13/4 is closer to pi than any other rational number with denominator 1, such as 2 over 1, 5 over 1, 6 over 1, and so on. So when b is equal to 1, we only need to show that p of a over b is true for 3 over 1 and 4 over 1. The two rational numbers in lowest terms with denominator b equal 2 that are closest to pi are 5/2 and 7/2. So when b is equal to 2, we only need to show that p of a over b is true for 5/2 and 7/2. The two rational numbers in lowest terms with denominator b equal 3 that are closest to pi are 8/3 and 10/3. So when b is equal to 3, we only need to show that p of a over b is true for 8/3 and 10/3. So instead of having to verify the propositional function p of a over b is true for all rational numbers with denominators b equal 1, 2, or 3, we only need to verify this for the 6 rational numbers that are closest to pi. We can do even better, however. Among these 6 rational numbers, we really only need to verify p of a over b is true for the 2 on either side of pi that are closest to pi. For instance, 3/1 is closer to pi than both 5/2 and 8/3. If we show p of a over b is true for 3/1, then it must be true for 5/2 and 8/3. Similarly, 10/3 is closer to pi than both 4/1 and 7/2. If we show p of a over b is true for 10/3, then it must be true for 4/1 and 7/2. We then only need to verify p of a over b is true for just 2 numbers, 3/1 and 10/3. These are the 2 numbers on either side of pi that are closest to pi. So we've reduced our domain for which we need to verify the propositional function from an infinite set all the way down to just 2 numbers. Finally, we're ready to actually verify the propositional function. P of 3/1 is the absolute value of pi minus 13/4 is less than pi minus 3/1. Since the absolute value of pi minus 13/4 is approximately 0.108407, and the absolute value of pi minus 3/1 is approximately 0.141593, then we can see that p of 3/1 is true. P of 10/3 is the absolute value of pi minus 13/4 is less than the absolute value of pi minus 10/3. And since the absolute value of pi minus 10/3 is approximately 0.191741, we can see that p of 10/3 is also true. And this proves our universal statement for all a over b, p of a over b. And thus 13/4 is a good approximation to pi. This example illustrates that we can sometimes use a proof by exhaustion even though the domain for the variable or variables is infinite. Now, even though 13/4, which is 3.25, is a good approximation to pi, according to the definition, it is still relatively far from pi. We can obtain better approximations to pi by finding good approximations with larger denominators. For instance, some other good approximations to pi, according to the definition, are 22/7, which is about 3.1428571, 333/106, which is approximately 3.1415094, and 355/113, which is approximately 3.1415929. This last approximation is accurate to 6 decimal places. The approximation accurate to 6 decimal places using the decimal expansion of pi is going to be 3,141,593 over 1 million, which has a denominator of 1 million. So 355/113 is much, much better as measured by the size of the denominator.